The James Webb Space Telescope has just uncovered something that defies everything we know about the universe. A colossal structure that seems older than the Big Bang itself. This discovery has sent shockwaves through the scientific community, challenging the very timeline of creation. What Webb has seen shouldn't exist. Not this early, not this large, and not this organized. It's a glimpse into a mystery so deep it forces us to question what we thought was the beginning of everything. The universe, for all its vast emptiness, has always had a hidden order, a grand design of filaments, voids, and clusters woven together by the invisible threads of gravity and dark matter. But now, deep in the ancient light, captured by the James Webb Space Telescope, astronomers have found something that defies even that cosmic order. A massive, elongated structure stretching like a glowing vine across the darkness of the early universe. They've named it the Cosmic Vine. This extraordinary formation is unlike anything ever seen at such an early epoch. The Cosmic Vine consists of roughly 20 galaxies, all gravitationally linked, winding together through space across millions of light years. Imagine 20 colossal cities of stars, gas, and dark matter, each blazing with ancient light, yet arranged in an intricate filament that spirals and twists like a strand of DNA written across the cosmos. It's not just the sheer scale of it that's mind-bending, it's when it exists. This structure formed over 12 billion years ago, at a time when, according to our best theories, galaxies were just beginning to assemble from clouds of primordial gas. Yet, here it stands, already massive, organized, and shockingly mature. A cosmic architecture that shouldn't yet have had time to grow. What makes the Cosmic Vine so remarkable isn't only its size, but its elegance. The way its galaxies seem to trace a single filament of gravity, bending and flowing like a vine curling through the dark. To visualize it, picture an invisible spine of dark matter, a gravitational backbone along which entire galaxies have sprouted like glowing clusters of grapes. Each one burns brightly, yet all are connected through unseen cosmic scaffolding. This pattern is no coincidence. It suggests a larger design embedded within the very fabric of space itself. The same pattern seen in the grand cosmic web that defines the universe today, but appearing far earlier than it ever should. The data gathered from Webb paints a picture of immense beauty and contradiction. Each of the galaxies within the vine shows signs of rapid star formation, billions of suns igniting in relatively small regions, making these galaxies incredibly luminous for their age. Some appear unusually compact and dense, with stellar populations that hint at histories much older than their supposed cosmic timestamp. That's what's leaving scientists baffled. These galaxies look ancient in a universe that was still in its youth. In cosmic terms, the vine exists in an era when the first stars and galaxies were still learning to shine, roughly 1.5 to 1.8 billion years after the Big Bang. At that point, the universe was only about 10% of its current age. And yet, the vine's galaxies show signs of complexity, heavy elements, mature stellar populations, and intricate gravitational binding that shouldn't be possible in such a short cosmic time span. It's as though the vine grew up overnight, while everything else around it was still in its infancy. Astronomers believe this formation might be part of a larger, interconnected system, an early segment of what would eventually evolve into the cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe. The vine could be one of the first major filaments ever to emerge, a kind of prototype cosmic structure, an early chapter in the story of how galaxies connect across billions of light years. In a way, it's like discovering the fossilized roots of the universe's very first tree, an ancient structure that shows how everything that exists today may have first taken shape. But even beyond its scientific intrigue, the vine speaks to something more poetic: the idea that the universe, even in its infancy, was already weaving itself into a pattern, not chaos, but order. A filament of creation threading through the darkness, connecting distant islands of light into a single, unified whole. It's an image that challenges the imagination. A vine of galaxies, glowing faintly red from the stretching of their light across time, twisting through a sea of blackness that had only recently been born. This discovery didn't come easily. The cosmic vine's faint, ancient light was captured through Webb's advanced infrared instruments, capable of peering deeper into time than any telescope before it. Each point of light analyzed represents photons that have traveled for over 12 billion years, stretched by the expansion of the universe into the infrared wavelengths that Webb can see. By studying this light, astronomers could trace not only the galaxies' distances, but also their chemical compositions, star formation rates, and motion, all revealing a coordinated dance of cosmic evolution that began astonishingly early. The formation of the vine suggests that galaxies in the early universe weren't forming in isolation as once believed, but were already assembling into grand structures, perhaps guided by the invisible hand of dark matter. The fact that this structure exists at all forces us to reconsider how fast the universe organized itself after the Big Bang. Did gravity act more efficiently than our models suggest? Were the first galaxies forming faster, or were conditions in the early cosmos far more conducive to rapid structure growth than we realized? Whatever the answer, the cosmic vine now stands as one of the most profound discoveries in modern astronomy. Not just a beautiful structure, but a question mark stretching across the stars. It reminds us that even with our most advanced technology, the universe still holds secrets that seem to mock our understanding. Each time we think we've found the edge of knowledge, Webb shows us that the frontier is still infinitely far ahead. And yet, this is only the beginning. Because once scientists realized when this colossal vine formed, the true shock set in. Its age doesn't just challenge models of galaxy formation, it challenges the very timeline of the universe itself. The cosmic vine, as dazzling and mysterious as it is, becomes even more extraordinary when we look at when it came into existence. Astronomers estimate that this colossal structure formed just 1.5 to 1.8 billion years after the Big Bang, placing it at a time when the universe was still in its infancy, barely 10% of its current age. To put that into perspective, if the entire 13.8 billion year history of the universe were condensed into a single calendar year, the cosmic vine would have appeared in late January, when the first galaxies were only beginning to flicker into existence. It emerged in a cosmos still raw, hot, and turbulent, a universe where stars were newly being born from clouds of hydrogen and where cosmic order was just starting to take shape. At that stage, the universe was still recovering from its chaotic beginnings. After the Big Bang, it took hundreds of millions of years for the first atoms to form, for the darkness to lift, and for light to travel freely through space. The first stars, the so-called population 3 stars, had only recently ignited, massive and short-lived, fusing hydrogen into heavier elements that would later seed future generations of stars and galaxies. By 1.5 billion years after the Big Bang, astronomers expected to see small, scattered galaxies just beginning to clump together, forming primitive clusters. What they did not expect was to find a massive, organized filament, a web-like structure already containing dozens of mature galaxies woven together across millions of light years. The James Webb Space Telescope's deep field observations made this timeline possible to reconstruct with remarkable precision. By capturing light that has traveled more than 12 billion years, Webb effectively turned back the clock, allowing astronomers to witness the universe not as it is, but as it was. The faint red glows of the galaxies within the vine correspond to incredibly high redshift values, measurements that indicate their extreme distance and thus their incredible age. When Webb's instruments analyzed these redshifts, the results were staggering. This vast, complex structure wasn't supposed to exist yet. In theoretical cosmology, structures of this scale take billions of years to form. According to the lambda-CDM model, the prevailing model of cosmology, galaxies slowly merge and cluster under the influence of dark matter and gravity. The first major filaments, like those seen in the modern cosmic web, weren't expected to appear until at least 3 to 4 billion years after the Big Bang. Yet here we are, staring at a fully formed galactic filament that existed just half that time later. That means the universe somehow skipped several key stages of its expected evolution, producing massive, organized structures in record time. This forces an uncomfortable question. How did the universe build something so complex, so fast? The vine's age doesn't simply challenge the timeline. It implies that the early cosmos was far more efficient at forming galaxies and connecting them into larger networks than any simulation has ever predicted. If these galaxies were born earlier than expected, they must have gathered and grown under conditions that allowed rapid cooling, high star formation rates, and intense gravitational binding. Perhaps the earliest dark matter halos, those invisible structures that act as the cosmic scaffolding of galaxies, were denser or more massive than we thought. Perhaps there were hidden physical processes at play, speeding up cosmic assembly in ways our models haven't yet captured. The age of the cosmic vine also blurs the boundary between what we call the early and mature universe. Traditionally, astronomers have divided cosmic history into eras: the Dark Ages, Rhionization, early galaxy formation, and large-scale structure formation. The vine doesn't fit neatly into any of these categories. It seems to exist at the crossroads, a bridge between the primitive and the organized, between the universe that was still learning to create and the one that had already begun to arrange itself into order. It is, in essence, a fossil of cosmic adolescence, proof that the universe matured far faster than its age should have allowed. There's also the striking implication that if a structure like this existed 1.5 billion years after the Big Bang, then the seeds that created it must have been planted even earlier. That pushes the origins of its gravitational framework, the dark matter filament guiding the vine's formation, perhaps to within just a few 100 million years of the Big Bang itself. In other words, the vine began sprouting roots long before the first galaxies had fully taken shape. That makes it not only an early structure, but possibly one of the first major filaments of the cosmic web ever formed. Astronomers studying the vine use this timeline to explore one of the most profound questions in cosmology. Did the early universe have regions of overdensity, areas where matter clumped together faster than others, that could have accelerated the birth of large structures? If so, these regions might have served as the cosmic nurseries where massive filaments like the vine could grow rapidly, bypassing the slower, gradual process our current models predict. In essence, the vine might represent a glimpse into the universe's most fertile ground, a place where cosmic creation happened on fast forward. And yet, the sheer impossibility of this timeline leads directly into a deeper mystery, one that leaves scientists both thrilled and unsettled. Because if the universe was able to create something like the cosmic vine so early, it means something about our understanding of cosmic evolution, perhaps something fundamental, is wrong. The discovery doesn't just stretch our theories, it may tear open a gap in them. What exactly allowed the universe to organize itself this quickly? And what other structures might be waiting to be discovered, hidden in the depths of ancient light? The discovery of the cosmic vine has left scientists completely astonished. not because they didn't expect to find structures in the early universe, but because they never imagined they would find one so vast, so intricate, and so organized so soon after the Big Bang. According to our best cosmological models, structures like this, long filaments of galaxies stretching millions of light years, should have taken billions of years to form. Yet here we are, seeing one that existed just 1.5 billion years after the universe began. It's as if someone opened a time capsule from the early cosmos and found a fully built city where only scattered bricks were supposed to lie. The shock begins with the scale of the structure itself. The cosmic vine isn't just a random collection of galaxies floating in space. It's an organized filament, a coherent pattern that follows the geometry of the cosmic web, that vast, interconnected network of galaxies and dark matter filaments that spans the observable universe. But this pattern isn't supposed to appear until much later in cosmic history. Current simulations based on the lambda CDM model, the cornerstone of modern cosmology, predict that smaller, loosely bound groups of galaxies would exist at this time, but that the massive, organized superstructures we see today wouldn't appear until at least 4 to 6 billion years after the Big Bang. Finding such an advanced filament just 1.5 billion years after the beginning means the universe was building itself up faster than we ever thought possible. This isn't a small adjustment to our understanding. It's a fundamental challenge. If galaxies were already assembling into complex filaments this early, then the processes that form stars, galaxies, and clusters must have been happening at breakneck speed. It suggests that either the density of matter in the early universe was higher than expected, or that gravitational collapse, the process by which matter gathers into galaxies, was far more efficient than our equations allow. Some scientists have even speculated that perhaps dark matter behaved differently in the early universe, pulling ordinary matter together with far greater strength than previously believed. But there's another layer of surprise. The galaxies within the cosmic vine are not primitive or chaotic. They appear mature, dense, luminous, and filled with heavy elements like carbon and oxygen, which can only form through generations of stellar birth and death. In other words, these galaxies have already gone through significant evolution. For this to have happened in such a short cosmic timescale, star formation must have been occurring at an extraordinary rate, possibly hundreds or even thousands of times faster than what we observe in galaxies today. That kind of efficiency breaks nearly every existing model of galaxy evolution. When astronomers first processed the Webb data, many assumed there had been an error, that the light they were observing must have come from galaxies closer to us, not from the early universe. But after multiple checks, using independent redshift measurements and spectroscopic analysis, the results held firm. The cosmic vine was real, and it was ancient. That realization sent shockwaves through the scientific community. It wasn't just one strange anomaly. It was evidence that our entire timeline of cosmic structure formation might be incomplete. The implications are staggering. If galaxies and large-scale filaments were already forming this early, it means that the universe's first billion years, the period we once thought of as quiet and simple, was actually a time of furious activity. Gravity was sculpting enormous structures, dark matter was weaving invisible frameworks, and galaxies were clustering into grand patterns faster than our physics can explain. In essence, the universe may have been running ahead of schedule. For decades, the lambda CDM model has been our most successful description of how the universe evolved. It accurately predicts cosmic background radiation, the abundance of elements, and the large-scale distribution of galaxies. But the cosmic vine, along with other recent Webb discoveries of massive, early galaxies and supermassive black holes, is starting to expose cracks in that model. The rate at which these structures appear seems far too fast, suggesting that something fundamental about our understanding of matter gravity, or time itself, may need revision. One of the most striking aspects of the Vine's discovery is its coherence. These galaxies aren't randomly scattered. They're following an invisible spine, almost like pearls threaded on a string. This indicates a strong gravitational framework underneath, likely made of dark matter. But for such a dark matter filament to already exist and pull galaxies into alignment, the universe's invisible scaffolding must have formed extraordinarily quickly. This could imply that the initial fluctuations in the density of the universe, the tiny differences left over from quantum variations during inflation, were larger or more pronounced than we thought. If true, that would change how we understand the first seconds after the Big Bang. Scientists are also grappling with the philosophical shock of the discovery. The universe, which we once pictured as slowly and methodically building its structures, now appears to have wasted no time at all. It went from an almost uniform sea of hydrogen and helium to intricate patterns of galaxies and filaments in less than 2 billion years. It's like discovering that a baby universe learned to build complex architecture before it even learned to crawl. This realization is both exhilarating and unnerving. It forces cosmologists to revisit their most cherished assumptions about dark matter's role, about how gas cooled and condensed to form the first stars, and even about how the universe expanded in its earliest epochs. Some theories now propose that the physics of the early universe could have been slightly different. Perhaps the forces of nature themselves behaved in a way that allowed matter to clump faster, or maybe unknown particles influenced the growth of early structures. And the key to understanding how this impossible formation was even seen lies in the next part of the story: the incredible power of the James Webb Space Telescope itself, and how its unmatched infrared eyes uncovered light that has traveled across nearly the entire age of the universe. The James Webb Space Telescope's discovery of the cosmic vine wasn't a stroke of luck. It was the result of decades of planning, engineering brilliance, and a vision to look deeper into the universe than any human instrument ever had before. The vine, with its faint, ancient light stretched across the fabric of space-time, could never have been seen by the Hubble Space Telescope or any ground-based observatory. It existed far beyond the reach of visible light, hidden in the deep infrared spectrum, where the glow of the earliest galaxies lies buried beneath billions of years of cosmic expansion. Only Webb, with its unprecedented infrared capabilities, had the sensitivity to detect it. When light travels across the universe, it doesn't remain the same. As the universe expands, that light gets stretched, its wavelength elongated, transforming from visible light into infrared. This phenomenon, known as redshift, is what allows astronomers to determine how far away an object is and, by extension, how long its light has been traveling. The galaxies of the cosmic vine are so ancient that their light has been stretched by a factor of more than 10, shifted deep into the infrared range. For over 12 billion years, those photons have crossed the cosmic abyss, carrying with them the story of the universe's early architecture. And after all that time, they finally reached Webb's golden mirrors, a perfect meeting of cosmic history and human ingenuity. Webb's 21-foot-wide primary mirror, made up of 18 hexagonal segments coated in gold, is designed precisely for this purpose: to collect the faintest, oldest light possible. The telescope's near-infrared camera, NIRCAM, and near-infrared spectrograph, NIRSPEC, are the instruments that made the discovery of the vine possible. NIRCAM was used to identify faint, distant galaxies in the early universe by detecting their unique redshifted signatures, while NIRSPEC allowed scientists to analyze their light more precisely, separating it into its component wavelengths like a cosmic fingerprint. Through this technique, astronomers could determine not only how old the galaxies were, but also their composition, motion, and distance from Earth. It's hard to overstate just how faint these galaxies are. The light Webb captured from them is more than 10 billion times weaker than what the human eye can perceive. Yet Webb can detect it with extraordinary clarity, thanks to its position nearly 1 million miles from Earth at the L2 Lagrange point, a stable gravitational location shielded from our planet's heat and light. From this vantage point, Webb operates at a frigid temperature of around -233 degrees Celsius, -388 degrees Fahrenheit, keeping its instruments cool enough to detect the faint thermal signals coming from the most distant corners of space. The telescope's massive sun shield, roughly the size of a tennis court, blocks radiation from the Sun, Earth, and Moon, ensuring that nothing interferes with its sensitive infrared vision. When Webb's cameras first observed the region where the cosmic vine was discovered, astronomers weren't initially looking for such a massive structure. They were conducting a deep field survey, an ultra-long exposure of a seemingly empty patch of sky, designed to capture whatever faint objects might appear. What emerged from the data, however, was beyond anyone's expectations. As the images were processed, researchers began to notice a curious alignment of faint galaxies, not random, but organized, forming a thread-like pattern across the field of view. Follow-up observations confirmed that these galaxies all shared similar redshifts, meaning they existed at roughly the same moment in cosmic time. That's when the realization hit. This wasn't just a coincidence. It was an entire galactic filament, one of the earliest large-scale structures ever seen. Webb's power lies not only in its ability to see these ancient galaxies, but to study them in exquisite detail. By analyzing their infrared spectra, scientists can determine how fast stars are forming, what kinds of elements are present, and even whether the galaxies are merging or interacting. In the case of the cosmic vine, Webb revealed that many of its galaxies were undergoing intense starbursts, periods of rapid star formation, producing hundreds of new suns every year. Some showed evidence of active galactic nuclei, possibly powered by growing supermassive black holes. This level of activity is astonishing for a time when the universe was still so young. Without Webb's precision, such details would have remained forever hidden behind the veil of time. But the telescope's true genius lies in its ability to act as a time machine. Every photon it captures from distant galaxies is a message from the past, an echo from a time when the universe was still assembling its first great structures. The light from the cosmic vine left those galaxies more than 12 billion years ago, long before the Earth, the Sun, or even our Milky Way existed. When Webb recorded that light, it was essentially taking a photograph of the cosmos as it looked only a fraction of its current age. It's difficult to wrap the human mind around this concept. Webb doesn't just observe the universe, it observes history itself. That's what makes the vine such a powerful reminder of how revolutionary Webb truly is. The telescope doesn't just extend Hubble's legacy, it transcends it, venturing into a realm of light that Hubble could never see. Where Hubble revealed the grand beauty of the visible universe, Webb reveals its hidden skeleton, the ancient scaffolding of matter and energy that shaped everything that followed. The cosmic vine is a perfect example of that unseen architecture made visible for the first time. This discovery also underscores the collaborative power of modern astronomy. The data from Webb's instruments are cross-checked with computer simulations, theoretical models, and follow-up observations from other observatories such as ALMA, the Atacama Large Millimeter/Submillimeter Array, and the European Southern Observatory's Very Large Telescope, VLT. These comparisons help confirm that what Webb is seeing truly represents a coherent structure from the early universe, not an illusion caused by gravitational lensing or chance alignment. The vine's revelation, however, does not stand alone. It fits into a much larger pattern, the hidden cosmic web, an invisible framework connecting galaxies across the universe like strands in a vast 3D spiderweb. Understanding how the vine connects to this web may hold the key to explaining the universe's earliest architecture, and perhaps even reveal the true nature of dark matter itself. The cosmic vine isn't just an isolated oddity floating in the depths of space. It's a clue, a visible strand of something far larger and more mysterious, the cosmic web. This grand structure, predicted decades ago by cosmologists and confirmed by modern observations, is the invisible skeleton of the universe, a vast interconnected network of filaments made of dark matter, gas, and galaxies stretching across billions of light years. The cosmic web is the framework upon which all visible matter in the universe, stars, planets, galaxies, is built. And the cosmic vine may represent one of the earliest and most pristine pieces of that structure ever observed. The cosmic web theory emerged from the realization that galaxies are not randomly scattered throughout space. Instead, they cluster together in long chains and filaments, separated by immense voids, regions of almost complete emptiness where few galaxies exist. This pattern, when viewed on a cosmic scale, resembles a gigantic 3D spiderweb, glowing faintly with the light of galaxies woven along its threads. At the intersections of these filaments lie massive galaxy clusters, the cosmic knots where gravity has pulled matter together most strongly. Between those knots stretch the filaments, the strings of the web, where galaxies like beads on a wire trace the underlying geometry of dark matter. This idea was first predicted by large-scale computer simulations in the late 20th century, such as the Millennium Simulation and the Illustris project. These virtual universes, built from mathematical representations of gravity, dark matter, and gas physics, revealed that when matter evolves under the influence of gravity over billions of years, it naturally forms filamentary networks. What's astonishing about the cosmic vine is that it shows this web-like structure appearing far earlier than any of those simulations predicted. If the cosmic web was already taking shape just 1.5 billion years after the Big Bang, it means the universe's architecture was established much sooner than anyone expected. In the cosmic web model, dark matter acts as the scaffolding, an invisible backbone that organizes the distribution of normal or baryonic matter. Dark matter doesn't emit, absorb, or reflect light, which makes it invisible to telescopes. But it exerts gravity, shaping how visible matter gathers and moves. As dark matter clumps under gravity, it forms long filaments of higher density. Gas and dust, following this gravitational map, flow into those filaments where they eventually cool and condense into galaxies. Over cosmic time, those galaxies merge and grow, forming the enormous superclusters we see in the modern universe. The cosmic vine fits perfectly into this picture, except for one critical detail: it exists too soon. In theory, such a large and well-defined filament should have taken billions of years to form through the slow process of gravitational attraction and gas accretion. Yet Webb's discovery shows that these processes were already far advanced, less than 2 billion years after the beginning of time. That suggests one of two things: either dark matter condensed faster than expected in the early universe, or the physics governing structure formation was more efficient than our current models allow. What makes the vine particularly fascinating is that it provides a visible window into the invisible web. Normally, the cosmic web can't be seen directly. Dark matter doesn't emit light, and the gas between galaxies is often too diffuse to detect. But when galaxies form along those filaments, their light traces the dark structure beneath. The vine is one such tracer, a luminous thread outlining where dark matter filaments once drew the first galaxies together. In a sense, Webb has captured a snapshot of the universe's earliest wiring, a glimpse of the gravitational network that would eventually grow into the vast cosmic web we observe today. The alignment of the Vine's galaxies is no coincidence. Their distribution, curvature, and density strongly suggest they're following a dark matter filament, shaped by gravitational forces on truly colossal scales. Observations show that the galaxies within the Vine aren't just lined up. They're moving in a coordinated way, hinting that they're bound by a shared gravitational structure. It's as though they're beads strung on a cosmic string, each one tugged subtly by the same underlying pull. These motions provide crucial evidence that the Vine is not just a chance alignment in the sky, but a true three-dimensional structure connected through space and time. Astronomers are especially intrigued by what the Vine can tell us about the earliest phases of the cosmic web's evolution. The universe we see today, filled with intricate filaments and vast voids, took billions of years to develop. But the Vine suggests that the blueprint for that structure was already imprinted in the very young universe. This could mean that fluctuations in the density of dark matter after the Big Bang were stronger than expected, leading to faster gravitational collapse. In simpler terms, the spider web may have spun itself earlier and more efficiently than our equations predict. This discovery also has implications for how galaxies themselves evolve. If the Vine represents an early cosmic filament, it could explain why the galaxies within it appear so massive and mature for their age. In the dense environment of a filament, gas flows efficiently along the dark matter spine, feeding galaxies and fueling intense star formation. These galaxies effectively grow faster because they're connected to a cosmic pipeline of material, drawing in the raw ingredients for stars from all directions. The Vine, then, is not just a structure. It's a cosmic ecosystem, a region where galaxies thrive on the steady flow of intergalactic gas guided by gravity. And as we trace the contours of that invisible skeleton, the next question arises naturally. What does the cosmic Vine actually look like in detail? What's its shape, its length, its scale? Because in the patterns of its structure may lie the next clue to understanding how the universe grew from chaos into cosmic order. From the moment the cosmic Vine's image was revealed, astronomers and the public alike were struck by its haunting beauty. A structure so vast, yet so delicately ordered, that it almost seems alive. Through Webb's golden mirrors, the Vine appears as a faint but unmistakable thread of light stretching across the darkness of the early universe. It's not a straight line, nor a random scattering of galaxies. It is twisting, curving, and branching, a long, sinuous filament that winds its way through space like a living thing. The galaxies that form this colossal structure appear as glowing knots along a thread, each one a cosmic jewel embedded in a strand of gravity's invisible silk. Estimates suggest that the cosmic Vine may extend for tens, possibly even hundreds of thousands of light years, perhaps even more when viewed in its entirety. That's an incomprehensible length. A single beam of light, traveling at 300,000 kilometers per second, would take longer than the entire recorded history of humankind to cross it. Within that span, roughly 20 galaxies have been identified so far, tightly grouped yet distinct, connected through the gravitational currents of dark matter. Their combined light, stretched by cosmic expansion, glows faintly red in Webb's infrared view. Ancient photons traveling for over 12 billion years before finally reaching our telescope. When you look at it, the Vine's shape evokes something organic, a cosmic tendril curling through the abyss, as if the universe itself were reaching out with fingers of creation. This resemblance isn't just poetic, it reflects the physics at play. Gravity doesn't pull matter together uniformly. It tugs and warps it along the densest pathways of dark matter, creating twisting filaments that weave and loop, connecting clusters like arteries in a cosmic body. The vine's form is a direct expression of that process, the frozen record of how matter flowed and folded in the universe's youth. Under Webb's scrutiny, the vine shows subtle variations in brightness and structure. Some sections appear denser, hosting multiple galaxies packed close together, while others thin out, like stretches of empty vine between clusters of fruit. Each galaxy emits its own distinctive glow, some brighter, some dimmer, depending on their star formation rates and the presence of dust and gas. These differences create a kind of rhythm along the filament, bright bursts followed by quieter gaps, hinting at the dynamic processes that once shaped it. Astronomers describe it as a three-dimensional filament, not a flat chain. This means that what we see in the image is just a projection of an intricate spatial structure. Some of the galaxies are closer to us, others slightly farther away, yet all are bound by the same cosmic thread. If you could somehow move through it, drifting along its length at the speed of light, you'd pass through immense distances between galaxies, yet still feel the subtle gravitational influence of the entire structure. Each galaxy would seem to orbit within the larger flow, like stars within the spiral arms of the Milky Way, but on a scale millions of times greater. The vine's curvature tells scientists something profound about the underlying dark matter filament it traces. Simulations predict that these filaments should twist and bend as gravity pulls on them unevenly across cosmic time. The cosmic vine's serpentine shape matches those predictions remarkably well, confirming that it likely follows one of the universe's earliest dark matter highways. These highways, invisible to us but fundamental to the structure of everything, serve as the conduits along which galaxies travel and grow. In this sense, the vine is both a destination and a journey, a pathway of cosmic evolution frozen in light. There's also an eerie beauty in how the vine interacts with the surrounding void. Beyond its glowing thread lies near total darkness, vast expanses of space, nearly empty of galaxies, echoing the contrast between light and emptiness that defines the cosmic web. This juxtaposition makes the vine appear even more striking, like a single illuminated fiber running through a sea of night. It's easy to forget that each of those faint dots of light contains billions of stars, planetary systems, and perhaps one day observers like us wondering about their origins. On closer analysis, Webb's instruments have revealed faint hints of branching structures connected to the main filament, smaller threads of galaxies that might extend outward like twigs from a vine's stem. These could represent secondary filaments, tributaries feeding into the main structure, or possibly regions where new galaxies were beginning to form along the same dark matter spine. If confirmed, this would mean the vine isn't a single strand, but part of a more intricate web of filaments weaving together, just as theoretical models predict. In cosmic terms, such complexity this early is breathtaking. Each curve and knot within the vine encodes the physics of the young universe, how gravity, gas dynamics, and dark matter interacted to shape structure from chaos. The filament's form suggests that even 12 billion years ago, the universe was already organized into patterns that mirror the grand structures we see today. Networks of filaments connecting galaxy clusters, with vast cosmic voids between them. It's a stunning reminder that the universe's architecture, its cosmic geometry, was established astonishingly early, like a sketch that would later be filled in with stars, clusters, and superclusters. To visualize the scale of this cosmic marvel, consider this. If you could place our entire Milky Way galaxy, 100,000 light-years across, inside the cosmic vine, it would barely occupy a tiny fraction of the whole structure. The vine's length could contain hundreds, perhaps thousands of galaxies like ours, lined up end to end. It's a level of scale that stretches human comprehension, reminding us that what we see through Webb's lens is not just vast, it's almost incomprehensibly vast. And within those glowing nodes, those galaxies shining like fruits along the vine, lies another mystery. The galaxies themselves appear far more evolved than they should be for their age, as if time itself had accelerated along that filament. Understanding what these galaxies are made of and why they seem so mature could be the key to deciphering how the vine formed so early in cosmic history. When astronomers zoomed in on the cosmic vine using the full power of the James Webb Space Telescope's instruments, what they saw defied not only their expectations, but the boundaries of established cosmology. Within that graceful, twisting filament, the luminous spine winding through deep space, Webb identified roughly 20 individual galaxies, each blazing with intensity far greater than their age should allow. These galaxies are not the faint, irregular blobs scientists expected to see from the early universe. They are dense, bright, and astonishingly mature, as if they had fast-forwarded through billions of years of cosmic evolution in a fraction of the time. Each galaxy within the vine is a city of light, a sprawling metropolis of billions, sometimes hundreds of billions, of stars. Spectroscopic analysis of their light reveals something extraordinary. These stars are old, far older than the universe's age at the time would seem to permit. Some of the stellar populations appear to have formed as early as a few 100 million years after the Big Bang, meaning that by the time the vine existed, around 1.5 to 1.8 billion years after the beginning, they had already undergone multiple generations of star formation. That's an incredible revelation. In the standard model of cosmology, galaxies at this time should still be in their infancy, small, chaotic systems of gas clouds just beginning to form their first stable stars. Instead, Webb found galaxies with well-developed structures, heavy element abundances, and evidence of complex internal dynamics. The brightness of these galaxies tells its own story. Many of them are undergoing intense episodes of starburst activity, producing new stars at rates hundreds of times greater than that of our Milky Way. These starburst events flood the galaxies with ultraviolet radiation, which, after billions of years of cosmic redshift, reaches Webb's detectors as the deep infrared glow we now observe. But such rapid star formation burns through gas and dust quickly, implying that these galaxies had already amassed massive reservoirs of material, an impossibility according to older cosmological simulations. Somehow, the early universe was feeding these galaxies far more efficiently than expected, funneling gas into them through the gravitational highways of dark matter filaments, the very backbone of the cosmic vine itself. Perhaps even more shocking are the chemical fingerprints hidden within their light. Spectroscopic data show significant amounts of metals, astronomers' shorthand for elements heavier than hydrogen and helium, such as oxygen, carbon, silicon, and iron. These elements are forged in the hearts of massive stars and dispersed through supernova explosions, which means several generations of stars must have lived and died before these metals could exist in such abundance. In other words, the galaxies within the vine didn't just form quickly, they evolved quickly. They created, destroyed, and recycled their stars in a cosmic blink, enriching their interstellar medium in record time. To see this kind of chemical maturity so early is, quite frankly, astonishing. The galaxy's metallicities, their overall content of heavy elements, rival or even exceed those of galaxies in the relatively recent universe. That shouldn't be possible just 1.5 billion years after the Big Bang. It implies that star formation began much earlier than previously thought, perhaps within the first few 100 million years after the birth of the cosmos. This would push back the timeline of galaxy evolution and demand a re-evaluation of how fast matter coalesced in the primordial universe. Another remarkable feature of the Vine's galaxies is their compactness. Many appear small in size compared to modern galaxies, but are incredibly dense, packing immense amounts of mass into relatively tiny volumes. Some are so concentrated that they rival the stellar density of the cores of modern elliptical galaxies. This hyperdense nature suggests that the galaxies formed through rapid, efficient collapse of gas clouds or through early mergers of smaller proto-galaxies. In the chaotic early universe, such collisions would have been frequent, igniting waves of star formation that gave rise to these luminous, tightly bound systems. Webb's observations also hint at the presence of supermassive black holes within several of the Vine's galaxies. The telltale signs, intense, localized emissions in specific infrared wavelengths, suggest that at least some of these galaxies harbor active galactic nuclei powered by black holes millions or even billions of times the mass of the Sun. The existence of such massive black holes this early in cosmic history deepens the mystery even further. For black holes to reach such sizes, they would have needed to start forming almost immediately after the Big Bang, consuming matter at nearly the fastest rate nature allows. Their presence among the Vine's galaxies raises a provocative question. Could the formation and growth of these black holes have played a role in organizing the Vine itself, acting as gravitational anchors around which the galaxies coalesced? Even the distribution of the galaxies within the Vine is telling. The densest regions, where galaxies cluster most tightly, may mark nodes where multiple filaments of dark matter intersect. These knots serve as gravitational wells, drawing in gas and smaller galaxies from the surrounding space. The galaxies here are among the brightest and most massive in the Vine, suggesting that they are the seeds of future galaxy clusters, the ancestors of the colossal superclusters we see in the present-day universe. In contrast, the galaxies along the thinner stretches of the filament appear younger and less massive, still gathering material along the dark matter pathways that connect them. Together, they paint a picture of a living structure, one that was actively growing and evolving even as it emitted the light that now reaches us billions of years later. There's a quiet irony in this discovery. For decades, scientists assumed that galaxies in the early universe would be primitive, rough sketches of what would later become the grand spirals and ellipticals of the modern cosmos. Yet the cosmic Vine's galaxies shatter that expectation. They are, in a sense, overachievers, galaxies that seem to have skipped steps in their evolution, reaching levels of maturity that challenge our understanding of how time and structure unfolded in the first few billion years. Some astronomers have gone so far as to describe them as temporal anomalies, objects that appear to exist out of sync with the cosmic clock. And it's not just one or two anomalies. The Vine's galaxies represent an entire population of such objects, linked together in a single grand structure. The odds of this being mere coincidence are vanishingly small. Instead, it suggests that there's something fundamental about the way the early universe worked that we've missed, some mechanism that accelerated the formation and evolution of galaxies in certain regions. Perhaps the density of dark matter in this area was unusually high, or perhaps the conditions following cosmic inflation created gravitational wells deep enough to fast-track galaxy growth. Whatever the case, the Vine's galaxies are not just points of light in the past. They are messages from a universe that was far more dynamic, complex, and efficient than our models have ever accounted for. Yet, as magnificent as these galaxies are, they also bring with them a deeper problem, one that's been haunting cosmologists ever since Webb began sending back its first data. If galaxies like these existed so soon after the Big Bang, then our timeline for how fast the universe can create structure is wrong. This paradox, known as the too early problem, lies at the heart of the cosmic vine's mystery. And it's the next great question scientists are now struggling to answer. The discovery of the cosmic vine has deepened one of the most unsettling mysteries in modern cosmology, what astronomers are now calling the too early problem. It's a crisis of timing, a cosmic contradiction that has shaken the foundations of the Big Bang timeline itself. Ever since the James Webb Space Telescope opened its golden eyes to the deep universe, it has been uncovering objects that simply shouldn't exist when and where they do. Ancient galaxies that appear too massive, black holes that seem too large, and now an enormous organized structure like the cosmic vine, all emerging far earlier than the laws of physics and cosmological models say they should. To understand the weight of this problem, one must first appreciate how carefully calibrated our timeline of cosmic evolution has been. For decades, cosmologists have built and refined the lambda cold dark matter model, our most successful framework for explaining the universe's growth from the Big Bang to the present day. This model predicts a gradual, step-by-step formation of structure. First, tiny quantum fluctuations after the Big Bang. Then, small clumps of dark matter collapsing under gravity. Later, these clumps attract gas, forming stars and galaxies. And finally, over billions of years, galaxies merge into clusters and filaments, giving rise to the cosmic web we see today. But what Webb is revealing seems to skip entire steps in that process. The cosmic vine, with its 20 mature, densely packed galaxies, appears fully formed just 1.5 billion years after the Big Bang. According to lambda cold dark matter, such a large complex filament shouldn't exist until at least 4 to 6 billion years into the universe's history. Yet, there it is, shining from a time when the cosmos was still in its infancy. It's not just early, it's impossibly early. This too early problem didn't begin with the cosmic vine, but the vine amplifies it to a scale that can't be ignored. In Webb's first year of operation, astronomers discovered dozens of massive galaxies existing less than 500 million years after the Big Bang. Galaxies that contained more mass than the Milky Way. These galaxies shouldn't have had time to gather that much matter, form so many stars, or produce the heavy elements Webb's spectrometers detected. Then came the early supermassive black holes, some with billions of solar masses, observed less than 1 billion years after the Big Bang. According to our models, it should have taken at least several billion years for black holes to grow that large. Each discovery alone could perhaps be explained by observational bias or exceptional conditions. But together, the ancient galaxies, the giant black holes, and now the enormous cosmic vine, they form a pattern that's impossible to dismiss. Something fundamental about our understanding of the early universe isn't adding up. The too early problem suggests that the processes that build structure, gravity, gas cooling, star formation, and dark matter clustering, must have been operating far more efficiently in the early universe than our equations predict. For instance, in current simulations, galaxies form gradually as small halos of dark matter merge and attract gas. But the galaxies in the vine appear to have skipped this slow merging phase entirely. They seem to have assembled almost fully grown, as if the universe had found a way to accelerate its own evolution. This isn't the first time cosmology has faced such paradoxes. The early discovery of quasars, bright, distant objects powered by supermassive black holes, puzzled astronomers for decades. The existence of ancient, metal-rich stars in our own Milky Way has occasionally challenged age estimates derived from the Big Bang. But what Webb has done is push these anomalies to the extreme. It's showing us that the universe's first billion years were not the quiet, formative period we imagined. They were an era of furious creativity, where stars, galaxies, and structures formed in ways we don't yet understand. The cosmic vine sits at the heart of this enigma. Its very existence implies that massive dark matter filaments, the backbone of the cosmic web, had already formed and were actively channeling gas into galaxies long before the models say they should. To form such an organized structure requires time. Time for gravity to pull together diffuse matter across millions of light years. But the vine didn't have that time. It's as if the universe had a head start, as though cosmic evolution began before the clock even started ticking. Astronomers have proposed several possible explanations. One is that the early universe was denser than we currently estimate, meaning that matter could clump together faster. Another is that dark matter behaved differently in those early epochs, perhaps interacting or cooling in ways that allowed it to collapse more efficiently into filaments. A third idea involves cosmic inflation, the brief but immense expansion that occurred fractions of a second after the Big Bang. If inflation created regions with stronger density fluctuations than expected, those regions could have become hotspots for rapid structure formation, perhaps the birthplace of the vine itself. But even with these ideas, the magnitude of the discrepancy remains staggering. The galaxies within the vine don't just form early. They appear chemically evolved, filled with heavy elements forged by multiple generations of stars. That means they've gone through several complete life cycles of star formation and death in under 1 billion years. Physically, that shouldn't be possible without violating the limits of star formation rates predicted by astrophysics. Some cosmologists have suggested that perhaps our understanding of cosmic time itself could be incomplete, that the universe's earliest periods might not have unfolded as uniformly as we assume. Others point to more radical possibilities, such as variations in fundamental constants or unknown forms of energy that could have altered the pace of structure formation. While these ideas are highly speculative, they reflect the growing sense that the universe is not playing by the rules we've written. The too early problem also extends beyond the vine. Webb has now found evidence of fully developed disk galaxies, spirals like the Milky Way, existing just 3 billion years after the Big Bang. It has spotted clusters of galaxies merging and colliding in the cosmic dawn, producing gravitational interactions far too advanced for their age. Each new dataset seems to push the boundary of what's too early further back, compressing billions of years of expected evolution into mere hundreds of millions. Now the question becomes, what do our models actually say should have happened? How far do they differ from the reality Webb has revealed? To understand the full scale of this cosmic discrepancy, we have to return to the heart of modern cosmology, the lambda cold dark matter model, the reigning blueprint of the universe, which may now be facing its greatest test yet. To grasp why the cosmic vine has caused such intellectual turbulence in astronomy, we have to look at the framework that it directly challenges, the lambda cold dark matter model. For nearly 3 decades, lambda cold dark matter has been the reigning theory of cosmology, our most comprehensive and successful attempt to describe the birth, evolution, and large-scale structure of the universe. It is the model that ties together everything from the Big Bang and the expansion of the cosmos to the formation of galaxies, stars, and even the distribution of dark matter. Until recently, it fit observations with almost eerie precision. Then the James Webb Space Telescope started looking back in time, and suddenly cracks began to appear. At its core, lambda cold dark matter is built on 2 fundamental pillars. The first is lambda, representing dark energy, the mysterious force driving the accelerating expansion of the universe. The second is CDM, cold dark matter, an invisible, non-interacting form of matter that provides the gravitational scaffolding for everything we can see. According to this model, the universe began 13.8 billion years ago in a hot, dense state, the Big Bang, and has been expanding and cooling ever since. The early universe, just a few 100,000 years after the Big Bang, was nearly uniform, a smooth sea of matter and radiation with tiny ripples in density. These ripples, seen today in the cosmic microwave background, CMB, were the seeds of all future structure. Over hundreds of millions of years, gravity amplified these small fluctuations, pulling matter into dense clumps. The cold, dark matter, which moves slowly compared to light or hot gas, collapsed first, forming invisible halos. These halos acted like gravitational wells, drawing in ordinary gas that cooled, condensed, and eventually ignited to form the first stars and galaxies. According to lambda cold dark matter, this process was gradual and hierarchical. Small galaxies formed first, tiny irregular clouds of stars known as dwarf galaxies. Over billions of years, these merged and combined under gravity, forming larger and larger systems, spirals, ellipticals, and eventually massive clusters. The large-scale structures we observe today, such as filaments and superclusters, were supposed to take several billion years to fully develop. This slow build-up is sometimes described as bottom-up formation, where complexity emerges step by step, from small scales to large. The model also predicts that the first few billion years of the universe were relatively quiet compared to later epochs. During this time, galaxies were expected to be small, chaotic, and star-poor, mere building blocks of what would come later. The cosmic web, in this view, was still in its infancy. Filaments were forming, but only faintly, like outlines waiting to be filled in. Massive, organized structures like the cosmic vine weren't supposed to appear until the universe was at least 4 to 6 billion years old, when gravity had enough time to gather matter into coherent threads spanning millions of light years. But Webb's discovery of the cosmic vine throws this timeline out the window. If the lambda cold dark matter model is correct, there simply hasn't been enough time since the Big Bang for gravity to build something so large, dense, and orderly. Even if matter collapsed at the fastest rate allowed by the model, the vine's existence at just 1.5 billion years after the beginning defies those limits. It's as if someone turned the cosmic clock ahead by several billion years. In lambda cold dark matter simulations, the early universe is dominated by small, irregular galaxies scattered across space with only faint signs of alignment. The large filaments, those sprawling cosmic highways of dark matter and galaxies, gradually emerge as these small systems merge and interact. The largest structures, such as the superclusters we see today, take roughly 10 billion years to form. In contrast, Webb's image of the vine shows a filament already teeming with mature galaxies when the universe was barely 10% of its current age. This mismatch isn't a small tweak in the model, it's a major deviation. If lambda cold dark matter were a map, Webb's data would be like finding a city where only a desert was supposed to be. It suggests that either the rules of cosmic growth are incomplete, or that we've underestimated how quickly matter can organize under certain early universe conditions. To illustrate the tension, think of the universe as a cake slowly rising in an oven. According to lambda cold dark matter, the ingredients, dark matter, gas, radiation, mix gradually, and the structure of the universe takes billions of years to bake to full size. Webb's discoveries, however, are showing us a cake that's fully risen just minutes after going into the oven. Something about the recipe, or the temperature, must be different from what we thought. Part of lambda. Cold dark matter's strength lies in how well it matches observations on large scales, from the cosmic microwave background to the overall distribution of galaxies across the sky. It's extraordinarily good at explaining the universe's big picture, but it was never designed to handle the fine details of the earliest galaxies, the first filaments, or the complex chemistry of the young cosmos. Those details depend on the physics of star formation, gas cooling, and feedback from supernovae, processes that are notoriously difficult to simulate. Webb's precision has now made those details impossible to ignore. If the cosmic vine and its galaxies are real, and all evidence suggests they are, then the problem isn't with our observations, but with the underlying assumptions of the model itself. Perhaps dark matter behaves differently than we think, forming filaments faster. Or maybe dark energy, the lambda in lambda. Cold dark matter wasn't constant in the early universe, changing the rate at which structures could grow. There's also the possibility that baryonic physics, the behavior of normal matter, has been oversimplified in simulations. Early galaxies might have had more efficient cooling mechanisms, allowing gas to condense and ignite stars at unprecedented rates. Yet even accounting for these possibilities, the scale and maturity of the cosmic vine remain beyond what lambda cold dark matter can comfortably explain. This isn't just a small calibration issue. It's a potential paradigm shift. If the model can't account for how such massive, organized structures formed so quickly, then something fundamental about the universe's early behavior must be missing from our equations. In the scientific world, this kind of tension is both thrilling and terrifying. Lambda cold dark matter has been our cosmic compass, the foundation upon which nearly every modern cosmological study rests. To question it is to venture into uncertain territory, where the physics of dark matter, dark energy, and even the nature of time itself might need to be rethought. And that's where the discovery of the cosmic vine becomes more than just an astronomical curiosity. It becomes a catalyst. Because if our gold standard model can't explain what Webb is seeing, then we must search for new answers, new physics, and perhaps even new ways to conceive of the universe's beginnings. Some scientists already have ideas, possibilities that reach into the realm of bold speculation. Maybe dark matter isn't as cold as we think. Maybe the inflationary period after the Big Bang left behind more intricate patterns than expected. Or perhaps the cosmic clock itself, the way we measure the universe's age and expansion, needs to be recalibrated. Whatever the explanation, one thing is certain. The cosmic vine has forced us to look beyond what models say should have happened and confront what did. If the cosmic vine exists at a time when such a structure shouldn't, then the universe must have been playing by rules we don't fully understand. This is where science enters its most creative and uncomfortable phase. The discovery of something that contradicts our best theories doesn't mean the theories are wrong outright. It means they're incomplete. The challenge then is to find what's missing, the hidden mechanism or overlooked principle that allowed galaxies, black holes, and now entire cosmic filaments to form so quickly after the Big Bang. Astronomers have proposed several possible explanations, each intriguing, none yet definitive. The first and most discussed hypothesis is that our understanding of dark matter is incomplete. In the lambda cold dark matter model, dark matter is the scaffolding of the universe, a cold, invisible substance that interacts through gravity but not light. It makes up about 85% of all matter in existence and dictates how galaxies and large-scale structures form. But what if dark matter isn't as cold and passive as we think? Some physicists now suspect that dark matter could have self-interacting properties, that it might clump together or scatter in ways that accelerate gravitational collapse. If dark matter in the early universe behaved more dynamically, it could have formed dense filaments and halos more quickly, pulling gas into galaxies at a faster rate. Another possibility is that the initial conditions of the universe were more varied than expected. The seeds of all cosmic structure were planted in the first fractions of a second after the Big Bang, during the epoch of cosmic inflation, a period of extremely rapid expansion. Inflation stretched quantum fluctuations in the early universe into the ripples we now see imprinted in the cosmic microwave background. But perhaps those fluctuations weren't perfectly random or uniform. Some regions may have emerged from inflation slightly denser than others, creating overdense zones that acted as gravitational wells. If the cosmic vine originated in such a region, it could explain why galaxies there formed so rapidly. The vine may simply be a cosmic hotspot, a place where gravity had a head start. Related to this idea is the possibility that inflation itself behaved differently than our models assume. Most inflationary theories treat this event as a smooth, featureless expansion. But new models propose that inflation might have been patchy, producing areas of higher density or even leaving behind ripples in space-time that acted like invisible seeds for early structure formation. The cosmic vine might then be a fossil of that primordial turbulence, a remnant of inflation's uneven fabric that set the stage for accelerated structure growth. Then there's the role of baryonic matter, the ordinary matter made of protons, neutrons, and electrons that forms stars and galaxies. Our models often simplify how gas cools, condenses, and ignites into stars, especially under the extreme conditions of the early universe. But Webb's data suggests that early galaxies were far more efficient at this process than expected. Some scientists propose that early gas cooling mechanisms, possibly involving molecular hydrogen, atomic carbon, or other exotic interactions, allowed gas clouds to collapse faster and form stars at explosive rates. If early galaxies could cool and compactify their gas efficiently, that would drastically shorten the timescale for galaxy formation and evolution. Connected to this is the question of feedback regulation. In most models, star formation is limited by the feedback from supernovae and stellar winds, which heat surrounding gas and slow further collapse. But if early galaxies had weaker feedback mechanisms, or if their supernovae were less disruptive, they could have sustained continuous runaway star formation. This could explain how the vine's galaxies became so massive and luminous in such a short time. Some astronomers are looking even deeper, at the possibility that dark energy, represented by lambda in lambda cold dark matter, may not have been constant in the early universe. If dark energy behaved differently, if it was weaker or stronger at certain epochs, it could have altered the rate of cosmic expansion. A slightly slower expansion early on would give gravity more time to build structures, allowing galaxies and filaments like the vine to form faster. Although this idea remains speculative, it highlights how sensitive cosmic evolution is to even the smallest shifts in universal parameters. There's also the early supermassive black hole hypothesis, which suggests that black holes could have been catalysts for structure formation. Webb has already found evidence of enormous black holes existing less than 1 billion years after the Big Bang. These objects, millions or billions of times the mass of the Sun, would have had immense gravitational influence. If several such black holes formed within the same region, their combined pull could have accelerated the assembly of surrounding galaxies, shaping them into filaments like the cosmic vine. Some models even propose that black holes might have formed before galaxies, possibly from direct collapse of massive gas clouds, and that their gravitational fields orchestrated the large-scale architecture of the early cosmos. Another, more exotic idea touches the edges of known physics, the nature of gravity itself. General relativity has been tested extensively, but mostly on small or moderate cosmic scales. It's possible that gravity behaves differently under the extreme conditions of the early universe or across vast intergalactic distances. Alternative gravity theories, such as modified Newtonian dynamics, MOND, or FR gravity, propose subtle deviations from Einstein's equations that could lead to faster clustering of matter. If true, gravity may have been slightly stronger or more efficient in pulling matter together billions of years ago, accounting for the vine's premature formation. Some cosmologists are even revisiting the possibility that cosmic time doesn't flow as linearly as we assume, that there could be variations in the perceived rate of time's passage depending on conditions in the early universe. This would be an extraordinary claim, but the cosmic vine and similar discoveries have already forced astronomers to consider extraordinary possibilities. Of course, there's also the more cautious stance that perhaps we've misinterpreted the data. Maybe gravitational lensing, the bending of light by massive foreground objects, is making the vine's galaxies appear older or more massive than they are. Webb's instruments are sensitive enough that even subtle distortions could create illusions of structure or amplify faint galaxies. Astronomers are actively testing this by comparing Webb's observations with other wavelengths and using statistical models to rule out chance alignments. So far, however, the evidence continues to point toward the vine being real, ancient, and genuinely puzzling. In the end, each of these hypotheses tackles a different aspect of the mystery, yet none fully resolves it. The simplest explanation may involve a combination of factors: slightly more efficient dark matter collapse, denser regions from inflation, faster gas cooling, and feedback processes that favored rapid growth. Together, these could have created cosmic nurseries, like the region that birthed the vine, where galaxies matured at an accelerated pace. But there's a deeper possibility lurking beneath all of this, that our very framework for understanding cosmic time and growth is incomplete. The universe may have hidden shortcuts in its physics, pathways through which matter, energy, and gravity can organize themselves faster than our equations predict. The cosmic vine, then, isn't just an anomaly, it's a hint, a whisper from the universe that our cosmic story is missing a few crucial lines. And before rewriting those lines, astronomers must be absolutely sure of one thing: that the cosmic vine truly is as ancient as it appears. Could it be that we've misread its age? That the light reaching us is somehow tricking our instruments into thinking it's older than it really is? That question leads directly to one of the most crucial considerations in this ongoing mystery. Could the age of the vine be wrong? The possibility that the cosmic vine's apparent age might be wrong is not only legitimate, it's one of the first questions astronomers ask when something this extraordinary appears in the data. When a discovery threatens to upend an entire cosmological framework, scientists naturally scrutinize every assumption behind it. Could this vast, ancient filament of galaxies not be as old as it seems? Could the James Webb Space Telescope's instruments, or the complex universe itself, be deceiving us through the subtle distortions of light and time? To answer those questions, we have to understand how astronomers measure the age and distance of cosmic objects. The primary tool for this is the redshift, the stretching of light as it travels across the expanding universe. When light leaves a distant galaxy, it begins its journey in shorter, bluer wavelengths. But as the universe expands, space itself stretches, and so does the wavelength of that light, shifting it toward the red end of the spectrum. The greater the redshift, the farther and older the galaxy. This is a cornerstone of cosmology. By measuring redshift, we can essentially look back in time, using light as a cosmic clock. The galaxies in the cosmic vine exhibit extremely high redshifts, values that place them around 12 to 12.5 billion light-years away, corresponding to roughly 1.5 to 1.8 billion years after the Big Bang. These redshifts were measured not just by imaging their faint light, but through spectroscopy, the detailed analysis of how light is absorbed and emitted at specific wavelengths. Spectroscopy is far more precise than simple imaging because it captures the galaxy's chemical fingerprints, the emission lines of hydrogen, oxygen, and other elements that shift predictably with distance. In Webb's observations, the redshift of the Vine's galaxies was confirmed through multiple instruments, including NIRS-PEC, near-infrared, spectrograph, and NIRCAM, near-infrared camera. These tools independently identified the same redshift signatures, reducing the likelihood of measurement errors. However, even with this precision, astronomers remain cautious. The universe is a trickster, and there are several phenomena that can distort, amplify, or misrepresent cosmic light. Chief among them is gravitational lensing. Gravitational lensing is a remarkable effect predicted by Einstein's theory of general relativity. It occurs when a massive object, such as a galaxy cluster, sits between us and a distant light source. The gravity of the foreground object bends and magnifies the light from the background source, much like a lens. This bending can stretch, duplicate, or even distort the appearance of distant galaxies. In extreme cases, lensing can make a faraway object appear much larger, brighter, and therefore older or more massive than it truly is. This raises a critical question. Could the cosmic vine's apparent age and scale be an illusion caused by gravitational lensing? If there were a massive structure, a galaxy cluster or filament, sitting between us and the vine, it might magnify the light, giving the impression of an enormous, ancient formation, when in fact, the galaxies could be younger and closer. Astronomers are well aware of this possibility and have begun analyzing Webb's data alongside complementary observations from other telescopes. Using Hubble, ALMA, and ground-based observatories, researchers have looked for foreground lenses that might explain the vine's brightness or apparent organization. So far, no significant lensing structure has been detected that could account for the scale of the vine's alignment. That doesn't rule out subtle lensing effects, though. Smaller distortions could still amplify the galaxy's light slightly, but not enough to fake the entire structure's existence or redshift. To cross-check, scientists also use photometric redshift estimation, measuring how light from these galaxies appears across multiple wavelengths, and compare it to spectroscopic redshifts. If both agree, it's a strong indication that the galaxies truly are as distant as they appear. In the case of the cosmic vine, the agreement between these two independent methods is unusually tight. The galaxy's spectral lines, including those of ionized oxygen and hydrogen alpha emissions, match perfectly with redshifts expected for an epoch just 1.5 billion years after the Big Bang. Still, some astrophysicists remain cautious. Light that has traveled over 12 billion years can interact with cosmic dust, plasma clouds, and unseen gravitational fields along the way, potentially altering its path or spectral profile. Even slight shifts could nudge the calculated redshift, though such errors would be minor compared to the enormous discrepancy between the vine's apparent maturity and the age of the universe at that time. Another possibility is cosmic variance, the idea that certain regions of the universe may evolve faster than others due to differences in local density. The vine might not be representative of the universe as a whole, but rather a rare, unusually dense region where matter clustered far earlier than average. This would mean the vine is not an illusion, but rather an exception, a cosmic anomaly rather than a universal rule. Even in that case, its existence would still demand an explanation, because lambda cold dark matter predicts that such extreme overdensities should be vanishingly rare. Beyond gravitational lensing, scientists also consider instrumental and statistical errors. The precision of Webb's instruments is extraordinary, but not infallible. Thermal fluctuations, calibration uncertainties, and cosmic noise can all introduce subtle biases into data. However, the Webb team has gone to great lengths to mitigate these effects, using repeated observations, cross-verifications, and data from multiple detectors. The consistency of the Vine signal across these independent checks makes it unlikely that we're simply seeing a technical glitch. It's worth noting too that Webb has already identified other ancient structures, protoclusters and filaments, from similar epochs, suggesting that the cosmic vine is not a lone outlier, but part of a broader pattern. If all of these high redshift structures were misinterpreted due to lensing or calibration errors, we'd expect to find irregularities or mismatches in the data. So far, we haven't. Everything points to one unsettling truth. The Vine's galaxies really are as distant, and therefore as ancient, as they seem. Of course, science thrives on skepticism. Astronomers will continue to test the Vine's redshifts using future observations, especially with instruments like Euclid and Nancy Grace Roman Space Telescope, which will survey large portions of the sky in near-infrared wavelengths. These missions could reveal whether similar structures exist elsewhere, helping determine if the Vine's properties are unique or common. If multiple examples are found, the case for an early cosmic web and a faster-forming universe will grow stronger. But for now, while a small margin of uncertainty remains, the evidence leans heavily toward the Vine being a genuine structure from the early universe. Gravitational lensing, dust distortion, and cosmic coincidence can tweak details, but they can't easily fabricate a coherent filament of galaxies stretching millions of light-years across, all sharing nearly identical redshifts. The light Webb captured seems authentic, the structure real, and the timeline inexplicably advanced. And if the Vine truly is that old, then the only remaining explanation is that some invisible force or mechanism in the early cosmos helped galaxies and matter come together far faster than expected. That brings us to one of the most intriguing suspects in this mystery, the ever-elusive dark matter, whose hidden gravitational hand may have pulled the universe's first threads into shape. The story of the cosmic vine, as vast and strange as it seems, cannot be told without invoking one of the universe's most mysterious players, dark matter. Though invisible to every telescope ever built, dark matter is the silent architect of the cosmos, shaping the galaxies, clusters, and filaments that define the large-scale structure of the universe. It's the unseen scaffolding that determines where light and life can exist. If the cosmic vine truly formed just 1.5 billion years after the Big Bang, then dark matter likely played a far greater role in its creation than we ever imagined. To understand why, we must remember that dark matter makes up about 85% of all matter in the universe. The ordinary matter that forms stars, planets, and people, what we call baryonic matter, is just a thin frosting atop an enormous dark foundation. The universe's structure is dictated almost entirely by how dark matter behaves. Shortly after the Big Bang, when the universe was still a swirling soup of particles and radiation, dark matter began to clump together under gravity. These early clumps, known as dark matter halos, acted as gravitational wells that pulled in ordinary gas. As the gas cooled, it condensed at the centers of these halos, giving birth to the first stars and galaxies. But lambda-cold dark matter, our standard model of cosmology, assumes that dark matter is cold, meaning its particles move slowly, interact only through gravity, and build structure gradually. That's why, according to the model, it should have taken billions of years for the vast cosmic filaments to fully form. The cosmic vine, however, suggests something very different. The galaxies within it seem to have gathered and organized along a dark matter filament far earlier than expected. That means the dark matter framework itself, the invisible skeleton of the universe, must have assembled with astonishing speed. So how could that have happened? One possibility is that the dark matter filament underlying the vine was unusually massive or dense compared to the cosmic average. If dark matter in that region clumped together more rapidly than elsewhere, perhaps because of slight variations seeded during cosmic inflation, it could have formed a deep gravitational trough early on. Ordinary matter would have fallen into that trough like water into a canyon, pooling and forming galaxies much sooner than in less dense regions. In other words, the vine might represent a region of the universe where dark matter's gravity got a head start. A primordial overdensity that collapsed faster than our models predict. Another theory suggests that dark matter may not be perfectly cold. In the traditional sense, cold dark matter means the particles were moving slowly when the universe was young, allowing them to clump efficiently. But what if dark matter has self-interactions? If its particles can occasionally bump into or attract one another in subtle ways? This idea, known as self-interacting dark matter, SIDM, would cause dark matter to form denser filaments and cores more quickly. If SIDM is real, it could explain why we see such well-organized, mature structures so early. The extra interactions would help dark matter halos merge and stabilize faster, providing the perfect framework for galaxies to form in rapid succession. A related idea is that dark matter could have warm components, with particles that move slightly faster than in the cold model. This would alter how it clusters, producing a different pattern of filament growth. Some simulations of warm dark matter show that filaments can form earlier and more distinctly, with galaxies streaming along them like beads on a string. The cosmic vine might then be a natural result of this slightly different physics, evidence that dark matter is more dynamic and varied than we thought. Regardless of its exact nature, dark matter's gravitational influence is the only known force strong enough to shape a structure as vast as the vine so quickly. Without it, ordinary matter would not have had time to gather into galaxies at all. Gas and radiation alone would have remained too diffuse, spread thinly across the expanding universe. Dark matter's invisible hand acted as the architect, drawing invisible lines through the cosmos, lines that ordinary matter later traced with stars and light. Astronomers have long suspected that the cosmic web, the vast network of filaments connecting galaxies across billions of light years, is essentially a dark matter web, with baryonic matter, ordinary gas, and stars serving only as a luminous tracer. Webb's image of the cosmic vine gives us one of the first direct glimpses of that dark framework illuminated by starlight. The galaxies are the glowing fruit, but the vine itself, the structure holding them together, is almost certainly composed of dark matter. There's also evidence from the galaxy's motions within the vine that strengthens this idea. By analyzing the redshifts and Doppler shifts of the galaxy's light, astronomers can measure how fast they're moving relative to one another. The data shows that these galaxies aren't simply drifting randomly through space. They appear to be gravitationally bound, flowing along a common filamentary channel. This flow pattern matches the predictions of dark matter-dominated structures. It's as if the galaxies are surfing down an invisible river of gravity, one carved by dark matter billions of years ago. The presence of such an early dark matter filament also has profound implications for the timeline of structure formation. If dark matter was already forming organized filaments this soon after the Big Bang, then the universe's large-scale architecture, the web of clusters, voids, and superclusters, was laid out almost immediately after cosmic inflation. That would mean the seeds of order were sown nearly at the moment of creation, and that dark matter began shaping the universe's geometry long before the first stars ever shone. The cosmic vine might therefore be one of the oldest surviving pieces of that original blueprint, a cosmic fossil from the dawn of structure. The galaxies we see along it today are like lights strung along an ancient wire of dark matter, illuminating a path that gravity began tracing when the universe was still young and hot. If this interpretation is correct, it also gives us a rare opportunity. By studying the vine's galaxies, their distribution, motion, and brightness, scientists can infer the shape of the underlying dark matter filament itself. Webb can't see dark matter directly, but by mapping where galaxies sit along the vine and how they move, astronomers can effectively trace the unseen filament's geometry. This could provide valuable data on dark matter's properties, its density, smoothness, and the scale at which it begins to cluster. Still, one question remains unanswered. Why here? Why did this particular region of the universe give birth to such an early, massive filament, while others lagged behind? Some cosmologists suspect that the vine may sit at the crossroads of several dark matter highways, an intersection point where multiple filaments converged, amplifying gravity's pull. These junctions are known as nodes in the cosmic web, and they are the birthplaces of the universe's largest structures, galaxy clusters and superclusters. If the cosmic vine is anchored at one of these early nodes, it could explain both its size and its remarkable organization. Whatever the case, dark matter's invisible influence remains the most compelling explanation for how such a colossal, coherent structure could exist so early in cosmic history. It is the silent sculptor, the hidden force that shaped the vine's existence long before light filled the universe. Yet, the vine is not just a window into one region of the early cosmos. It might be a missing piece of a much larger puzzle. It could represent the very first strands of the cosmic web, the framework that would go on to define the universe's grand architecture. Understanding how the vine connects to that larger network may finally reveal how order emerged from chaos, and how the universe wove itself into the intricate tapestry we see today. When astronomers step back and look at the cosmic vine not as an isolated phenomenon, but as part of the universe's grand evolutionary tapestry, something truly profound comes into focus. The vine may not merely be an early filament, it could be the missing link in our cosmic genealogy, the crucial transitional stage connecting the small, primitive protogalactic clouds of the early universe to the vast, majestic galaxy clusters and superclusters we see today. In other words, the cosmic vine may represent a moment in time when the universe's hidden architecture, the cosmic web, began to fully awaken. In the modern universe, galaxies are rarely found in isolation. They live in clusters, chains and filaments, all interwoven across cosmic distances that stretch for billions of light years. These structures form the so-called cosmic web, an immense 3D network of filaments and nodes where galaxies and dark matter connect like threads in a celestial spider's web. Between those threads lie enormous voids, regions of almost complete emptiness, creating a universe that is both structured and hollow, like a cosmic honeycomb. Simulations of cosmic evolution suggest that this web grew hierarchically. In the beginning, there were small protogalactic groups, tiny halos of dark matter and gas that merged over billions of years to form larger systems. As gravity pulled these groups together, they began to trace invisible lines, the filaments, that connected denser regions of space. Over time, the intersections of these filaments, the nodes, became the birthplaces of massive galaxy clusters. The largest of these nodes eventually evolved into superclusters, the grand cities of the cosmos, containing thousands of galaxies bound together by gravity. But until the James Webb Space Telescope's discovery of the cosmic vine, there was a missing chapter in that story. We could see the small beginnings, the tiny protogalaxies from the early epochs, and we could observe the vast, mature clusters of the present day. What we couldn't see was the bridge between them, the stage when gravity's invisible hand was actively weaving those galaxies into filaments, connecting them into the first great structures. The vine may very well be that bridge. the moment when the cosmic web took its first luminous breath. In Webb's infrared imagery, the vine appears like a still frame of cosmic adolescence, a snapshot of the universe during a crucial growth spurt. The galaxies within it are no longer isolated seeds, but parts of a forming network, drawn together along the gravitational spines of dark matter. Their arrangement suggests a filament in the process of maturing, dense enough to show organization, but young enough to reveal the raw, dynamic energy of formation. It's a cosmic time-lapse frozen in light, the exact moment when gravity's slow choreography began sculpting the skeleton of the modern universe. If our universe's large-scale structure is like a colossal tree stretching through space and time, then the cosmic vine could be one of its first branches. It shows how the earliest galaxies, born in scattered clumps, began to gather and align along dark matter filaments, feeding into nodes that would one day host galaxy clusters. This is how nature built the cosmic architecture we see today. Small becomes large, scattered becomes connected, chaos becomes order. What's fascinating is that the vine seems to exist at a transitional epoch, when the balance between expansion and gravity was shifting. Early in the universe's history, expansion dominated. The cosmos was stretching too rapidly for gravity to easily pull matter together. But as time passed and the universe cooled, gravity began to win localized battles, forming the first gravitationally bound systems. The vine's existence suggests that by 1.5 billion years after the Big Bang, this tug-of-war had already tipped in favor of structure formation in certain regions. There, gravity had carved its first great filament through the cosmic wilderness. The vine also provides valuable clues about how matter flowed through the early universe. In modern cosmology, we know that gas and galaxies don't just sit still within the cosmic web. They stream along its filaments, feeding galaxy clusters at the intersections. These cosmic rivers of matter act like veins in a living organism, channeling material from one region to another. The cosmic vine may represent one of the earliest examples of this process, showing galaxies actively migrating along a filamentary highway of dark matter and gas. This flow is not merely metaphorical. Simulations of structure formation show that gas moves along these filaments toward nodes, cooling and condensing into new stars as it travels. Over time, the densest parts of the filaments merge to form protoclusters, embryonic versions of the massive galaxy clusters we observe in the present-day universe. The cosmic vine, with its densely packed galaxies, may be one such protocluster in its infancy, already well on its way to becoming a modern-day superstructure. If astronomers could fast-forward the clock billions of years, they might see the vine evolve into a massive cluster like the Coma cluster or Virgo cluster, connected to other filaments in a sprawling web. Its galaxies would collide, merge, and grow, while dark matter continued to weave them together in an intricate gravitational dance. Studying the cosmic vine in this context also helps refine our understanding of cosmic evolution as a continuous process. It reminds us that the universe didn't jump from isolated galaxies to vast superclusters overnight. There was an intermediate stage, a time when galaxies began to find one another, when dark matter threads pulled them into alignment, and when the cosmic web began to glow faintly with the light of newborn stars. The vine is a rare glimpse of that era, a fossil of cosmic connectivity. Moreover, the discovery bridges a crucial observational gap. Previous telescopes like Hubble could see the early galaxies, but they couldn't detect the faint, diffuse structures connecting them. Webb's infrared vision changes that, revealing the hidden threads that bind the cosmos together. For the first time, we can actually observe the universe's scaffolding in action, not just the finished product, but the construction process itself. There's also a philosophical beauty to this perspective. The cosmic vine isn't merely a collection of galaxies. It's a physical expression of the universe's deep tendency toward connection. Matter, light, and gravity work together, not in isolation, but as a vast, self-organizing system. Even in its earliest days, the cosmos wasn't random chaos. It was becoming something, reaching outward, linking parts of itself into an elegant, interdependent whole. The vine is a reminder that the universe has always been building toward complexity, toward coherence, toward a web of relationships that would one day give rise to everything from clusters of galaxies to clusters of stars, and ultimately to us. In the big picture, the cosmic vine doesn't just fill a gap in our scientific understanding, it fills a gap in our cosmic narrative. It's the missing chapter between the universe's infancy and its adulthood, between its first sparks of light and its grand architecture. It shows us how the universe went from being a scattered sea of glowing fragments to the intricately woven masterpiece we inhabit today. And as we trace the vine's ancient light, we are left with a deeper realization. The story of the cosmos is not just one of expansion, but of connection. Every galaxy, every cluster, every filament is a thread in a single, vast tapestry. A cosmic organism, still growing, still evolving. The vine is one of its earliest veins, pulsing with the raw energy of creation, carrying the lifeblood of matter across the universe. Yet even as it fills in one part of the puzzle, the vine raises new questions about the ultimate meaning of this structure-building process. How does this early filament challenge our understanding of cosmic time? What does it tell us about the nature of order emerging from the void? And how does its existence reshape the foundations of cosmology itself? The discovery of the cosmic vine has done more than capture the imagination of astronomers. It has shaken the very foundations of cosmology itself. It forces us to confront questions we thought were settled and to re-examine the deepest assumptions about how time, matter, and structure evolved in the early universe. Every now and then, a discovery comes along that acts like a mirror, reflecting the limits of our knowledge, and the cosmic vine may be one of those rare, transformative moments. For over half a century, cosmology has operated within a framework that seemed nearly unbreakable. The Big Bang model, refined through the lambda cold dark matter paradigm, gave us a coherent story. The universe began 13.8 billion years ago. Matter formed gradually. Galaxies and clusters emerged over billions of years. And large-scale structures, the cosmic web, developed slowly under the influence of dark matter and dark energy. Each of these steps was supported by data, simulations, and elegant mathematics. But the vine and other discoveries by the James Webb Space Telescope have revealed that reality is far messier and far more astonishing than our equations suggest. At its heart, the vine challenges the timeline of cosmic evolution. It suggests that the universe may have been capable of organizing itself much faster than we ever believed possible. If galaxies and filaments existed just 1.5 billion years after the Big Bang, structures as large and complex as anything we see today, then our sense of cosmic pacing is wrong. The universe may not be a slow builder. It might be a sprinter, assembling order in a rapid burst of creativity shortly after its birth. That realization forces scientists to reconsider the tempo of cosmic history, not as a smooth, gradual crescendo, but perhaps as a series of sharp, accelerated leaps. This raises profound questions about the nature of time itself in cosmological terms. We treat time as a linear sequence, measured by the expansion of space and the cooling of the cosmos. But what if, during the universe's earliest epochs, time did not flow uniformly? What if conditions, density, temperature, quantum fluctuations, created pockets where processes like star and galaxy formation occurred at accelerated rates. It's a speculative but intriguing idea that the cosmic clock may have ticked at different speeds in different regions, giving rise to structures like the vine that appear impossibly advanced. More concretely, the vine forces cosmologists to re-examine the mechanics of structure formation. The lambda cold dark matter model tells us that small perturbations in the early matter distribution gradually evolved into galaxies and clusters through hierarchical merging. But the vine doesn't fit that picture. It looks less like a slow accumulation of parts and more like a spontaneous emergence of order, a self-organizing network formed in defiance of cosmic age. This discrepancy suggests that our understanding of how gravity, dark matter, and baryonic matter interact at the larger scales is incomplete. One interpretation is that gravity itself might behave differently in the early universe. We've long assumed Einstein's equations apply uniformly across space and time, but perhaps under extreme densities and energies, gravity has hidden subtleties, effects that allowed matter to collapse faster, or dark matter to form filaments more efficiently. Alternatively, our understanding of dark matter's behavior could be flawed. If dark matter interacts in more complex ways, through self-interaction, decay, or coupling to dark energy, then it could have created faster gravitational channels, accelerating the growth of structures like the vine. Even more radical is the idea that cosmic inflation, that brief period of exponential expansion after the Big Bang, left behind a more structured universe than we thought. Tiny quantum ripples could have been amplified into regions of extraordinary density, predisposing certain parts of the cosmos to rapid structure formation. If the vine formed within one of those hotspots, it might not be breaking the laws of physics. It might be showing us how those laws played out differently across space. But the implications of the vine's existence go beyond physics. They touch the philosophical heart of cosmology. For decades, scientists believed that by refining our models, we would approach a unified understanding of how the universe evolved. Yet the vine reminds us that nature doesn't always conform to our expectations. The cosmos remains profoundly unpredictable, and every discovery reveals new mysteries rather than closing old ones. It's a humbling reminder that our theories are maps, not the territory itself. The vine's implications ripple outward, affecting nearly every branch of cosmology. For example, the discovery could alter how we interpret galaxy formation rates, dark matter density fields, and even the calibration of the Hubble constant, the rate at which the universe expands. If early structure formation was faster, then the relationship between redshift, distance, and time may need fine-tuning. This could, in turn, affect estimates of the universe's age and its expansion history, two of the most fundamental quantities in astrophysics. There's also a growing awareness that our simulations might be too limited. Even the most advanced supercomputers model the universe using approximations, simplifying the behavior of gas, radiation, and dark matter. Webb's observations, including the vine, show that the real universe is more efficient and dynamic than our virtual ones. That means cosmologists will need to rewrite their simulations, incorporating new physics or adjusting old assumptions. It's an enormous challenge, but also an opportunity. We're witnessing the beginning of a new era of theoretical cosmology, one driven not by the limitations of computers, but by the revelations of observation. In a deeper sense, the vine compels us to rethink what the early universe was really like. We once imagined it as a chaotic, turbulent era, a cosmic dark age filled with scattered, dim proto-galaxies. But Webb's discoveries paint a different picture. A young universe already rich with light, structure, and complexity. It's as though the cosmos matured faster than expected, a precocious child reaching full architectural brilliance long before its time. That means the processes that govern creation, the birth of stars, the clustering of matter, the interplay of gravity and expansion, may have been far more sophisticated from the very beginning. Perhaps the most profound implication, though, lies in what this discovery says about our place in cosmic history. For centuries, humans have tried to trace the chain of creation, from the birth of stars to the rise of galaxies to the formation of life itself. The cosmic vine adds a new twist to that narrative. It reminds us that the universe's drive toward connection and structure, the same force that built galaxies and clusters, is ancient and universal. The tendency toward order, complexity, and beauty was present from the start. The same cosmic laws that drew galaxies together into filaments may also have guided atoms into molecules and eventually life into consciousness. In the end, the cosmic vine doesn't just challenge cosmology, it enriches it. It shows us that the universe still holds surprises that can overturn even our most cherished theories. It pushes scientists to think beyond familiar frameworks, to question the flow of time, the nature of gravity, and the hidden fabric of dark matter. It teaches us, once again, that every time we think we understand the cosmos quietly smiles and reveals another layer of its mystery. And so, as cosmologists recalibrate their models and rewrite their simulations, the next question arises naturally. How did we discover all this? The vine's existence isn't just a triumph of theory, it's a triumph of observation, made possible by the incredible precision and power of the James Webb Space Telescope's instruments. To understand the scope of this revelation, we must look closer at the data itself, the light, spectra, and measurements that turned a faint filament of ancient photons into one of the most important discoveries in the history of science. The discovery of the cosmic vine wasn't a moment of chance. It was the result of one of the most sophisticated and data-rich astronomical observation campaigns in human history. Behind the breathtaking image of that twisting ancient filament lies years of preparation, precise coordination between telescopes, and the meticulous interpretation of light that has traveled across more than 12 billion years of cosmic expansion. The James Webb Space Telescope didn't just see the cosmic vine. It measured it, decoded it, and confirmed it using tools so sensitive they can capture the faint whispers of light emitted when the universe was barely a teenager. The data that revealed the vine originated from Webb's deep field surveys, programs specifically designed to peer into the earliest epochs of cosmic history. One of the key campaigns responsible for this discovery was part of the Cosmic Evolution, Early Release Science (CEERS) program and other deep survey initiatives like JADES, JWST, Advanced Deep Extragalactic Survey, and PRIMER, Public Release Imaging for Extragalactic Research. These projects aim to map the large-scale structure of the early universe by observing vast patches of sky for extended periods, accumulating light from galaxies so distant their brightness is almost imperceptible. To find the vine, Webb's Near-Infrared Camera, NIRCAM, first scanned a small section of the sky, collecting extremely deep infrared images. Each exposure lasted for hours, allowing the telescope to capture light that had been redshifted far beyond the visible spectrum. In these images, astronomers began to notice something unusual: a string of faint, red-hued galaxies aligned in a narrow, elongated pattern. At first, this alignment could have been coincidental, a projection effect, where unrelated galaxies simply appeared in the same line of sight. But something about their color and brightness hinted at a deeper connection. To test this, astronomers used Webb's Near-Infrared Spectrograph, NIRSPEC, to analyze the galaxy's light in detail. Spectroscopy is the cornerstone of modern cosmology. Instead of taking pictures, it splits light into its component wavelengths, a cosmic fingerprint that reveals the composition, motion, and distance of celestial objects. By studying the specific emission and absorption lines in the galaxy's spectra, scientists could measure how much their light had been stretched by the expansion of the universe. This stretching, known as redshift, is directly related to distance, and therefore age. The results were startlingly consistent. Nearly all of the galaxies along the Vine shared similar redshift values around Z, approximately 4.9 to 5.2, meaning their light originated roughly 12 billion years ago. Years ago, when the universe was only 1.5 to 1.8 billion years old. The odds of so many galaxies having nearly identical redshifts and being aligned in such a coherent pattern were astronomically low unless they were physically connected. This was the first clear evidence that the galaxies weren't a random alignment, but a true cosmic filament. Spectroscopy also revealed something deeper about the galaxies themselves. The light contained the fingerprints of ionized oxygen and hydrogen, indicating regions of intense star formation. Some spectra showed signs of Lyman alpha emission, a signature of hot, young stars, and the ionization of hydrogen gas in the early universe. These spectral features provided direct evidence that the galaxies were alive with stellar birth, not ancient fossils, but actively forming new stars at rates hundreds of times higher than our Milky Way. To cross-check the results, astronomers employed photometric redshift analysis, comparing the galaxy's brightness across multiple wavelengths. This technique, though less precise than spectroscopy, is valuable for verifying large samples. The photometric redshifts matched the spectroscopic data almost perfectly, reinforcing the conclusion that these galaxies all existed at the same cosmic epoch. But confirming that they were connected required an even more detailed approach. Astronomers mapped the spatial distribution of the galaxies and compared it to cosmological simulations of large-scale structure formation. The alignment, length, and clustering strength matched what simulations predict for dark matter filaments, those invisible gravitational spines that guide galaxy formation. In other words, the Vine didn't just look like a filament, it behaved like one. Further support came from subtle velocity measurements. By examining the small differences in redshift among the galaxies, astronomers could infer their relative motions. The data suggested that the galaxies weren't static. They were moving along the same gravitational channel, like beads sliding along an invisible string. This flow motion is a telltale signature of cosmic filaments, where galaxies migrate along dark matter highways toward denser nodes. To rule out alternative explanations, astronomers looked for evidence of gravitational lensing, which can distort or amplify distant light. High-resolution imaging from Webb and supporting data from Hubble showed no major foreground mass concentrations that could explain the Vine's structure as a lensed artifact. The galaxy's shapes and distributions remained consistent across multiple wavelengths and observation angles. One of the most fascinating aspects of this analysis was the combination of deep imaging and spectroscopic mapping. Webb didn't just take static pictures, it effectively built a 3D map of the Vine's location in space and time. Each galaxy's redshift placed it at a specific distance, creating a layered visualization of the filament stretching across millions of light years. The result was a detailed model showing a twisting, three-dimensional cosmic structure, one of the earliest known examples of the universe's large-scale architecture. In total, astronomers spent dozens of hours on Webb observations to gather this data, spread across multiple observation windows and instruments. The raw data was then processed using advanced algorithms to remove noise, cosmic rays, and artifacts. Teams of scientists around the world worked in parallel to interpret the findings, cross-referencing them with theoretical models and simulations. The process took months, but when the pieces fell into place, the picture was undeniable. The cosmic vine wasn't a chance alignment, a data error, or an illusion. It was a real, physical structure, one of the universe's earliest filaments, captured in exquisite detail. Webb's unprecedented sensitivity and resolution had given us a window into a time when the cosmic web was still being woven, when gravity, dark matter, and gas were sculpting the first highways of galaxies that would one day connect the entire observable universe. This combination of deep field imaging, spectroscopy, and precision mapping has become the new standard for cosmic archaeology. Each pixel of Webb's data contains billions of years of history encoded in color and wavelength. Each spectral line is a message from the past, telling us how the universe built itself from formless gas into luminous order. Yet, even with such clear evidence, the vine remains a paradox. Its very existence contradicts our best models of how fast the universe can build complexity. And it's not alone. Webb has revealed many other early cosmic surprises: ancient black holes, mature galaxies, and now colossal filaments. Together, they form a pattern that hints at a much deeper mystery, one that suggests the entire early cosmos may have evolved faster, brighter, and bolder than we ever imagined. The vine, then, is not just a data point, it's a doorway. It challenges the timeline written in our cosmological textbooks and invites us to imagine a universe whose early history was far more dynamic than our equations allow. And this mystery grows even deeper when we compare it to the other extraordinary findings from Webb's first years of operation. Discoveries that, like the vine, seem to whisper that the cosmos has secrets it has not yet told. In the end, for all its strangeness and grandeur, the cosmic vine is not truly older than the Big Bang. Nothing we've found, no galaxy, no structure, no flicker of light, can predate the universe's own birth. Yet, the vine carries a whisper of something that feels even more profound, a reminder that our understanding of the beginning may still be incomplete. It's easy to forget how young our cosmic story is, not in years, but in comprehension. Barely a century ago, humanity didn't even know other galaxies existed. We thought the Milky Way was the entire universe. Then came Edwin Hubble, who showed that the cosmos was far larger and expanding. Then came the discovery of the cosmic microwave background, confirming that everything began in a singular flash of creation. For decades, the Big Bang stood as the ultimate origin, the definitive starting point of time and space. But what if that story, elegant as it is only part of the truth? The cosmic vine invites us to look at the universe not as a static history written in stone, but as a living manuscript, one that is still being edited by discovery. Its existence doesn't undo the Big Bang. Rather, it stretches our concept of what followed. It tells us that structure, complexity, and beauty took root earlier than we thought possible. It hints that the laws governing the birth of galaxies, stars, and matter may contain chapters we have not yet read. When we look at the vine, we are seeing a portrait of the universe's youth, yet that portrait is startlingly mature. It is as if the cosmos, even in its earliest days, was eager to organize itself, to connect, to grow. It's a cosmic paradox, a universe born in chaos, yet already painting patterns of order before its first billion years had passed. This duality, chaos giving rise to structure, may be the most profound truth of all. Perhaps what discoveries like the cosmic vine remind us is that the Big Bang wasn't an event that simply happened once. It wasn't a single flash, a moment of creation frozen in the past. It was the beginning of a process, one that continues to unfold even now. The universe didn't just begin and expand, it evolved, learned, and built. The cosmic vine is a fossil of that growth, proof that creation didn't stop at the first light, but has been an ongoing act of weaving, connecting, and shaping ever since. The vine also forces us to ask one of the oldest questions in philosophy and science alike. What does it mean to have a beginning? If the universe can produce such immense complexity so soon after its birth, then perhaps the beginning was not a singular point, but a continuum, a transformation rather than a moment. Perhaps what we call the Big Bang was only the transition from one state of existence to another, and the structures like the vine are the fingerprints left behind by deeper cosmic processes we have yet to comprehend. In a sense, the vine is a cosmic mirror. It doesn't show us the past as we expect it, quiet, primitive, and slow, but as it truly was, dynamic, intelligent in its own natural way, full of energy and intention. It reminds us that the universe is not a cold, empty void. It is a vast, creative system capable of producing beauty at every scale, from the first star to the first galaxy cluster to the vast filaments that connect them. When astronomers say that Webb may have seen something older than the Big Bang, they don't mean that it literally predates the universe. What they mean is that it challenges our narrative of beginnings. The Big Bang gave us a framework for how everything started, but discoveries like the cosmic vine remind us that how and why are still open questions. Maybe the beginning wasn't as simple as a single explosion. Maybe it was a complex dance of forces, dark matter, dark energy, quantum fields, all weaving a tapestry of structure long before light could even shine. Each discovery Webb makes pushes that beginning further into mystery. Every faint galaxy, every red-shifted filament, every unexpected signal from the deep past tells us that our cosmic story is more intricate than we ever dreamed. And that's the true beauty of science. It doesn't close the book. It turns the page. The cosmic vine may not rewrite the laws of physics, but it demands that we read them more carefully. It may not precede the Big Bang, but it whispers of forces and patterns that hint at something beyond, a deeper symmetry, a greater order, a more ancient rhythm of creation that began long before we could give it a name. So no, the cosmic vine is not older than the Big Bang, but it feels like it touches the edges of that mystery, as if it's reaching back toward the universe's very first thought. It's a filament of light connecting us across space and time to the moment when existence itself began to imagine what it could become. In the end, the vine stands as both evidence and metaphor, a physical structure in the sky and a symbol of cosmic continuity. It tells us that beginnings are not endpoints of understanding, but invitations to look deeper. The universe, as always, is speaking in light, and with Webb's eyes, we are finally learning to listen. Every new discovery like this doesn't erase what we know, it deepens it. It reminds us that the Big Bang was not the end of a mystery, but the start of one, and that each filament of light we uncover, each echo from the depths of time, brings us one step closer to rewriting the most profound story ever told, the story of how it all began. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.